One of nature's most powerful elements is the ocean currents. Transporting billions of cubic meters of water every second, they are a key element in stabilizing the world's climate. We base all our living conditions on a stable climate, but man-made influences or drivers are now changing the climate, and these changes may cause change to the ocean currents.
We want to understand the physics behind it. We want to formulate that in a model, and we want to make the predictions and see how it will change in the future, given the boundary conditions like increased CO2 emissions and other things like that.
Well, the Thor project has been given us basically a prediction system. A prediction system which can tell you for the next 10 years, at least for the North Atlantic, how climate may change there.
What we are mostly concerned about is that there is a certain threshold which is then reached, a certain point where there's a kind of point of no return, more or less.
One of the biggest surprises is that the ocean and the thermohaline circulation respond to these external drivers within just a decade.
We know that the oceans and their distribution of heat from the equator to the poles plays a major part in keeping the temperatures of the northern part of Europe stable. And we know that the oceans absorb by far most of their energy from the sun, and that deep currents are distributing the accumulated heat from the hot oceans at the lower latitudes to the high north, creating a climate that is stable and fit for humans. The transport of warm ocean water is, to a high extent, driven by the mechanism in the Arctic. We also know that human activity is affecting the climate, and that the ocean currents are reacting to these changes. What we don't know is how these drivers will affect the strength of thermohaline circulation, on which almost all Europeans are basing their living conditions.
90% of the people living in the Northern Hemisphere, 50 degrees north, are living in Europe and in Russia. So if you change the climate, then these people will have no more crops to live on, and they have to move. So there will be a gigantic migration of people when the climate is changing here. So that's why we should be interested in the stability of our local climate.
Human activity, such as the massive burning of fossil fuels, has led to a change in the composition of the Earth's atmosphere, and hence to a change in the Earth's temperature. Extreme events such as flooding, heat waves, extreme rain and storms are all suspected to be a consequence of the ongoing climate change. The question is how these man-made drivers are affecting the ocean currents in the future, and how the change of the currents may interact with the atmosphere. This is why we have established the Thor project, which is a cooperation between 9 European countries. The common goal is to be able to identify and predict the mechanism that controls the main distributor of heat into the European oceans, the THC, or the thermohaline circulation.
We've got 22 different research groups from 9 different nations. Involved are the Nordic countries, but also France, Germany, the Netherlands and England.
The Thor project has enabled us to gain a deeper understanding of the mechanism that controls the THC, and furthermore, how these mechanisms interact with each other. The ongoing observation is integrated into a surveillance system, which can operate as a weather forecast for the climate 15 to 25 years ahead. That system can give us the chance to adapt to changes.
We are developing these forecast models or forecast tools. We are also working on developing a sustained observational system with minimum effort of instrumentation but maximum output. In order to do that, we have to understand the physics of the system. How are the ocean currents in the mean? How are they varying? And what kind of measures do we have to take to get an estimate of the strengths of the circulation?
The THC, thermohaline circulation, is publicly known as a part of the Gulf Stream. It consists basically of 2 currents. One is a subtropical gyre of warm surface water, a giant horizontal swirl that circulates clockwise. Part of this water heads northeast and forms 2 branches, one heading towards Scandinavia, crossing the Greenland-Scotland ridge, and the other toward northern Canada. As these waters cool, they sink and flow south at great depths, down the western edge and the Atlantic basin. This circular movement means that warm water is transported close to the European mainland, and for centuries, this mechanism has secured a mild climate in the northern part of Europe, providing stable living conditions for more than 400 million people.
The North Atlantic THC is a system of currents where you have a flow in the upper layers going northwards, sinking, and going southwards in the deep layers. And we are talking about something like 15 to 20 million cubic meters per second, which means, in other words, it's 15 to 20 times as much water as all the rivers in the world.
Without the movement of these massive columns of water, the planet would be extremely warm near the equator and deep frozen from the poles and much of the landmass. Yet our knowledge of these giant sub-ocean currents is far from sufficient. But what we know is that if any change in their stability should happen, Europe as we know it will no longer be the same. So we are searching for new ways of understanding the main stabilizer of the European climate.
We need to have observations in order to be able to understand the system, be able to be sure that nature is the way we think it is. So if you want to predict the future, you need to have observations to be sure that the models that you use to predict are correct.
Our present observations tell us that at the present stage there are no massive changes in the THC, at least looking at the European side of the system. So why do we need to continue and further develop the surveillance of the system? For more than 40 years, researchers have been working on examination how climate and ocean currents have interacted, and from core samples from deep ocean sediments, we know that the THC does react to changes in the atmosphere. Based on this data from sediment samples, the researchers have reproduced the history of the THC development thousands of years back in time. They have tested their data on the climate models we already have.
We have been out at sea and we've been collecting marine sediment core from the deep ocean. We targeted specific areas in the North Atlantic that we know are sensitive location to study the thermohaline circulation and sea surface temperatures. And we use sophisticated methods to extract this geochemical information. And with that we can reconstruct temperature, we can reconstruct salinity and ocean variability and nutrients back in time.
When we compare the results of the sediment observations from the ocean with the observations of temperature in the atmosphere back in time, we can see that the two curves follow each other closely. This tells us how the THC has responded directly to changes in the atmosphere in the past.
We know from historical data that over these two climatic events, the medieval warm period, which is a long stable warm period in Europe, and the Little Ice Age, which is a well-known described historical event, that the temperature changed. And our big question is, does the ocean also respond on this very short time scale? And one of the major results, and maybe also one of the biggest surprises, is that the ocean and the thermohaline circulation respond to these external drivers within just a decade.
On board research vessels, the researchers have conducted measurement on temperatures, salinity, current flow, and scanning of the ocean bed in order to get a better picture of the system's dynamic.
This cruise has been proposed to collect a number of data autonomously, for example, the temperature. So we record the temperature at certain depths at fixed locations, and then currents to see how fast the water is flowing at these depths, and salinity, which is another important parameter for us in oceanography because it influences the density of the water. And the density, on the other hand, is important for the whole energy of the marine system, of the physical system of the ocean.
Since 1960, there have been measuring instruments deployed over a line from the Labrador Strait to the Faroe Islands and Scotland.
What we are mostly concerned about is that there is a certain threshold which is then reached, a certain point where there's a kind of point of no return, more or less. So we will have a trend where it gets warmer and warmer and warmer, and then there will be no return from this warming. So it will continue to warm, and that will change the whole system, the whole flow of the system, and maybe, for example, the thermohaline circulation may be changed.
Increased observations alone are not able to extend our prediction capability of the THC behavior. High-resolution models are needed to extend the value of the observations and create a deeper understanding of the total system's future behavior.
Models are a way to try to improve our knowledge of the processes that can control and explain the present state and the future of the THC. And this better understanding is very important, because if we don't understand the THC, we cannot predict the THC.
The predictability is based upon a more detailed understanding on how the different components interact, and this is what the models can tell us.
One of the interests that you can have in running models is that you can, in a sense, disconnect parts of the mechanistic of the ocean, disconnect parts of those and see how the links work between the different parts. So doing so, you can discriminate between the action of one part on the other and the feedback of the other part on the first one. So models can help you, and one of the strategy of THOR is to use at the same time couple models. By couple, I mean coupled ocean-atmosphere model and standalone model. And doing these parallel experiments, you're able to extract what is the role of the ocean, the feedback of the ocean onto the atmosphere and onto the climate.
So by isolating different parameters, we have created a deeper understanding of the interaction of the THC, the ocean, atmosphere, and the future climate. These new high-resolution models are the first tool we need to create before we can design a reliable forecast system.
I think the THOR project, what it achieved in terms of modeling is it set up what we call a multi-model decadal prediction system. So a number of the big climate models from centers around Europe, they got together, they used the same kind of setups, and differently than before, we used the current state of the climate to predict into the future. And that has been really new, that we didn't do that before in IPCC, we didn't do that before in any other project. We tried it in previous projects, but now we really established such a multi-model system. So we can use our models now to look 10 years ahead and see how the thermohaline circulation changes in those 10 years and what its wider impacts are on climate, because we calculate the ocean, but we also calculate the atmosphere at the same time.
With the present state of our models, we can actually look into the future. The next step is to find out where to look for the drivers that now are pushing our present climate balance and integrate the impact of these drivers into the models. Where we see the first and most massive change of climate change is in the polar regions, where the THC has its main driving engines. Freshwater, river runoff and ice discharge is now changing the ocean's composition. The Greenland inland ice alone is now discharging more than 210 cubic kilometers of ice into the Arctic waters every year.
The major threats we see right now against the thermohaline circulation mainly derives from the Arctic region. We see increased melting from the Greenland ice sheet. We see a retreat of Arctic sea ice. We see large reorganizations in the Arctic Ocean system which accumulates freshwater. All of these things are components which may affect the thermohaline circulation.
The factors that are important for changes in conditions in the thermohaline circulation are first of all the warming of the climate itself, which is induced partly by human activities, by the greenhouse gases we emit. It has a further impact, the greenhouse gas emissions and the warming, is that at the higher latitudes there will be more rainfall and there will be melt. And those conditions really change the stability of the thermohaline circulation.
Density of the water is a key factor for the THC driving mechanisms. When the surface water is cooled down in the Arctic, it becomes denser, and when the salinity rises, it sinks to the ocean bed. This is the main engine that runs the THC. But now more fresh water is entering the Arctic Ocean, and when this is integrated into the models, a new development of the engines is revealed. In a warmer climate state, the engine of the Labrador Sea seems to simply collapse.
We tend to lose one of the two drivers of the system, so we have a more sensitive system now which only relies on one engine, and that means that the risk for something more dramatic to happen must increase. And that is one of the things we spend a lot of time in Thor using our models to try to address this increased risk of something to happen.
This increased risk is now something we need to consider as a fact today. With the increased melt, ice discharge and precipitation, we have a strong need to predict what can happen to the second engine, the North Atlantic Deepwater Formation.
We have in Thor made a set of experiments where we add additional freshwater into the North Atlantic system. That should mimic the increased melting from the Greenland ice sheet, but could also mimic other sources of freshwater like a cascade of freshwater out of the Arctic Ocean. And we see a lot of changes in the subpolar Atlantic in particular. We see a near collapse of the convection in the Labrador Sea, but the situation is more delicate when we move to the Nordic seas and consider the last of the deep water sources. But also in warmer climates, many of our model systems predict that it can resist even strong pulses of fresh water from the Greenland ice sheet and will continue to feed deep water into the North Atlantic and act as a driver of the thermohaline circulation.
Given the importance of the THC and looking into the present driver that can potentially change the stability, we can begin to understand why we should expand our understanding of the models into forecast systems. If we can establish a warning system that tells us when changes are happening, we can react to these changes and adapt to the new situation in time. But how far are we from turning our models into this, a predictable warning system?
So in the Thor project today, we can clearly say, based on the modeling experiments and the reconstructions that we've done, that the ocean responds very strongly to external drivers over these timescales. The Little Ice Age as a good example. It's the most modern wobble in the climate system that we have. Taking this knowledge now, we can put that knowledge into future models and start playing with the drivers that will be driving the future climate in the world. There will be more volcanism, there will be changes in solar intensity, but additionally, we also have man-made drivers like increased CO2 in the atmosphere. Basing our knowledge on what we know of how the ocean responds on natural timescales, we can use this into giving much more accurate predictions of what could happen in the future.
So we have developed these tools. We know how with the uncertainties of course, but a pretty good measure how the climate will develop. And this is the basis for decisions to be taken for society, by the society and by the politicians. The future doesn't look black. It's not like in Hollywood movie where we all of a sudden get an ice age. This is not going to happen. But we have to be aware of these influences that human behavior has on the climate, and we are now able to predict what is going to happen if we behave in a certain way.